A mathematical reason to expect that real data will be normally distributed is a theorem called the central limit theorem, which is one of the most important results in statistics. The central limit theorem says that almost any data that is an average of the effects of many random influences tends to be normally distributed. And since real data is often some sort of average of the effects of many random influences, real data does tend to be normally distributed. For example, average daily temperatures, such as the data shown in this plot, is affected by sun and wind and clouds and the complex dynamics of the atmosphere, and so average daily temperature is an example of a measurement that is expected to be normally distributed because it is the accumulated effect of a large number of effectively random influences. Similar observations apply to a lot of data. Stock prices, for example, and the fractional day-to-day changes in prices shown in this plot are subject to investor psychology and current events and market forces and a variety of other influences, and so, like the weather, financial data is also often expected to be normally distributed. In realistic examples, individual influences like current events and sun and wind and so on are often difficult or impossible to measure, or often are simply unknown, and so to see more clearly how the central limit theorem really works, it's instructive to consider artificial examples where the individual random influences can be seen explicitly. For example, consider collecting data that is an average of variables that individually have a distribution like the distribution shown here, called a uniform distribution. The measured data could, for example, be the average voltage for a collection of batteries or the average price for a set of products where the individual prices or voltages are uniformly distributed between minimum and maximum values. This input uses the random variate function to draw n equals 2 random values from a uniform distribution. This computes the average of two uniformly distributed random values. This makes a table of 25 of those averages, and this makes a histogram of 1,000,000 of those averages. So this is the distribution of values in the measured data. This particular histogram is the distribution of the mean of n equals 2 uniformly distributed random variables. According to the central limit theorem, as the number n increases, this distribution gets closer and closer to a normal distribution, and that does indeed happen in this example. If n is increased from 2 to 10, for example, this distribution is almost indistinguishable from a normal distribution. Something similar will happen for almost any distribution of the individual variables. For example, this shows the distribution of averages for n equals 10 variables where instead of being distributed over a continuous range, the individual variables can only have values 1 or 2, which is a distribution called a Bernoulli distribution. Since the individual variables are discrete, the distribution of averages will also only have certain discrete values. As the value of n gets larger, however, the histogram of averages fills in the spaces in the range and the distribution of averages gets closer and closer to a normal distribution. So the common requirement in statistics that the data be normally distributed is often not much of a limitation, since a lot of real data is normally distributed, or at least has a distribution that is close enough to a normal distribution that common statistical methods will give useful results.